Section 3 is important on one hand, not so much in another. That's because we're going to focus upon the theoretical foundation here, so it's going to be important for the students who are seeking some in-depth learning, especially those who are going for graduate school. On the other hand, for exam preparations, not very much, because you're not going to do a lot of problem solving here. All you need to know is the end result here, which will be used in problem solving in the next section. In any case, here we go. The general solution theorem. The general solution of a nth order homogeneous linear ODE looks like this. We have n linearly independent solutions and form a linear combination c1y1 plus c2y2 and so on, all the way up to cnyn. That is the general solution. Can there be some other form? No, not really. That's something we'll have to establish. How about non-homogeneous case? Yp is a solution, a particular solution of this non-homogeneous equation, then the general solution is always in this kind of form. The solution for homogeneous part plus that particular solution. And the homogeneous part is of course c1y1 plus c2y2 all the way up to cnyn. And these c1 through cn's can be determined using the, the initial condition. So we have system of linear equations, n equations and n unknowns. We can get those done, and then we'll have a unique solution. Is there any other form? No, not really. In the end, what we're going to use is this one, the fundamental theorem. You see, you have uniqueness. So no matter what method you use, if you establish one, that is the solution. So that's how we have this linear combination form, and then YH plus YP form. That's something everybody have to remember. Now, another thing that everybody has to remember is principle of superposition. Let's talk about it. The first half is rather trivial. If you have the solutions of homogeneous equation, y1 through ym, not necessarily n, m and n can be different, and also y1 through ym need not be linearly independent. They could be independent or maybe not, it doesn't matter. In any case, if they are homogeneous, if they are solutions of homogeneous equations, then their linear combination is also a solution. That's actually easy to see, so let's talk about it. How do you prove it? Well, let's set the left-hand side of the ODE as L of y of t, and it's linear in a sense that all the additions can be separated. Yes, we have nothing but addition and the derivatives, and then multiplication by coefficients. So yes, it does work out. And then what do we put? c1y1 plus c2y2 all the way to cmym, excuse me. Okay, all right. And then the linear combination and the nth derivative of the linear combination. Repeat that and take n minus first derivative, n minus second derivative, all the way to first derivative, and then no derivative here. Add them all up. Now let's use the property of the derivative. Derivative of sum is equal to sum of the derivatives. Repeat that for all the derivatives. Then basically you have the derivatives. Now we can change the order. Here an times c1, and then next an minus 1 times c1, and so on, all those y1 part put together. Then what do you get? c1 times nth derivative of y1, an minus 1, and n minus first derivative of y1, and so on and so forth. All the y1 part here. And what is this? this just left-hand side of the ODE. So that's 0. Repeat that for y2, y3, and ym, the last one. Again, this is the left-hand side of the ODE, so that's 0. So what did we have? We just have a bunch of zeros added together, so this is 0. In other words, this is also a solution of a homogeneous equation. So even if you just add or multiply by coefficient or take linear combination, 0 remains 0. Okay, how about non-homogeneous case? This superposition is a little bit more important. Okay, here we go. And we have yp1 and yp2. We have two equations and two solutions. Excuse me, let me rewrite it in that regard. Okay. Oops. Okay, that's better. So yp1 is a solution of first non-homogeneous equation. yp2 is a solution of the second non-homogeneous equation. Then y of t is a solution of this homogeneous equation given by adding these two together if and only if y is sum of those particular solutions plus the homogeneous. That's a principle of superposition. Basically, you're adding up these particular solutions, superpose, and then you can always add 0, so that too follows as a matter of fact. You can multiply something here as well, but then again, it's okay because the homogeneous part, this one, already includes the scalar multiplication. You see, they all have C1 through Cm already in there, so additional multiplication here is not really necessary. Okay, how do you prove that? Well, it's easy, but this is for if and only if, so you have to be a little bit careful. Let's talk about one direction, but before that, for simplicity, let's put L of y as the left-hand side of that ODE, this part, okay? All right. And then let's prove one direction. Let's suppose y is a solution. Then what? So L of y, the left-hand side, is equal to f1 plus f2. Okay, it's a solution, so it satisfies this one. Then let's put y minus yp1 minus yp2 into the same equation here. Then what do you have? We have nothing more than just a bunch of additions and then multiplying by coefficient and taking a derivative any number of times. So you can simply separate all these additions. And what is this? L of y, because this is a solution of this original equation here, this is f1 plus f2. And then yp1, that'll give me f1. yp2, that's going to give me f2. So we have f1 plus f2 minus f1 minus f2. Oh, that's 0. So this whole thing is equal to 0. That's a homogeneous equation. So this whole thing is actually a solution of homogeneous equation yh. So we have it. Simply flip over this part. Then what do we have? We have the solution. Y equals to yh plus yp1 plus yp2. How about the other direction? Let's suppose y is given by yh plus yp1 plus yp2. Okay, and then plug everything into this and use the same idea. We have nothing more than just a bunch of addition and multiply by coefficient and taking the derivative, so we can separate all the additions. YH, that'll give you 0, and YP1, that'll give you f of 1. yp2, that's going to give you f of 2. So what do you get? 0 plus f1 plus f2, same as what we want. So we have it. So we had some elementary proof, but do I regard that proof really important? As a matter of fact, not really. I mean, it's neither significant nor ingenious. But the end result, the superposition itself, everybody should know. And same goes to this general solution theorem. General solution can be written as a linear combination. Everybody has to know. Non-homogeneous case, homogeneous part plus particular part. Everybody has to know. As for the rest of the subsections in this section, let's divert it to a separate video, which probably will not interest a lot of people. This one, we stop now.